All right, this is video 15 for the baby burial analysis series, and continuing our discussion on sequences. And the last video we covered subsequences, and we particularly talked about the monotone subsequence theorem, which said every sequence has a monotone subsequence. Then we talked about the Bolzano-Weierstrass theorem, which says every bounded sequence has a convergent subsequence. Now, to add to this, which I didn't mention last time, was that there's a theorem, and this theorem's, I guess, pretty important. So you have a bounded sequence. The sequence yn converges if and only if every subsequence y and k converges to the same limit. So that's an important theorem. Now, because of this, then the sequence diverges if and only if there are two subsequences y and k and ymk, where y and k converges to L and ymk converges to M, and L does not equal M. In other words, you have it diverges if you can produce two subsequences that converge to two different limits. All right, so I didn't mention that last time. So it is required that all subsequences converge to the sum L and the real numbers in order for the sequence yn to converge as well. All right, so now we're going into Cauchy sequences, and a lot of this information that I'm going to discuss is presented from the Real Analysis textbook by J. Cummings. So I would say see J. Cummings Real Analysis textbook, long form mathematics textbook. All right, that's what all of the following is going to be taken from. Remember at the beginning of the course, I said there were two main texts, and one of the texts was using the Real Analysis textbook by Bartle, 4th edition, and this Real Analysis textbook, long form mathematics textbook by J. Cummings. And very rarely I might talk about Rudin's principle of mathematical analysis, which I probably get to Rudin towards the end of this baby real analysis series. Okay, so for Cauchy sequences, note that some sequence an converges to A if and only if for all epsilon greater than 0, there exists a natural number such that for all little n bigger than capital N, the distance between an and A is less than epsilon. All right, that's just our standard definition for a sequence to converge. Now, what if we don't know what, and also this whole thing depends on if we know the limit at A. So what if we don't know the limit A? Can we still determine if the sequence converge? One proposition, or one way to think about it that you might come up with is, well, if once we know the sequence, like when it converges, we know that the terms get closer and closer together. When you get infinitely close to the sequence, right? So if I had like some sequence A1, A2, AN plus 1, AN plus 2, and so forth, we know, let me do another one, AN plus 3 for the subscript. So we know all of the n's in which the sequence is within epsilon distance of the limit are these ones. So these are all the n's bigger than capital N, where the distance between an and the limit a is less than epsilon. So if we don't know a, but we still want to determine the sequence converges, it might make sense to think of that as I keep going further and further, the distance between each term is getting arbitrarily small. So it might make sense to think of the distance between consecutive terms like an plus 1 minus an plus 2, and then like an plus 2 minus an plus 3, and so forth. It might make sense to think of these getting arbitrarily small. They need to be within epsilon distance. All right, that's a reasonable guess as far as a way to determine if it converges, but we don't know what it converges to. We know that when it does converge, that all of these n's that are bigger than capital N are within an epsilon distance of the limit a. But if we didn't know a, at least I think it might make sense that the distance between each consecutive term is getting arbitrarily smaller. All right, that might be a reasonable way of looking at it as far as figuring out how to determine if a sequence converges without knowing the limit. But is it enough to say that this sequence converges, if the distance of an plus 1 minus an gets arbitrarily small? So that's the question. In other words, whenever a sequence converges, each term is deviating less and less from the previous term. The jumps are tending towards 0. If consecutive terms are getting closer and closer together, does that mean the sequence converges, is the question. And again, I note this is all taken from J. Cummings' Real Analysis Long Form Mathematics textbook. A lot of the stuff I cover in these series is from jumping from his stuff, along with Bartol's Real Analysis, along with my own sort of notes. But in particular, I will say this Cauchy sequence stuff, J. Cummings words it beautifully, so that's why I'm pretty much citing him for this. So it might be reasonable to think that the distance between each consecutive term after you've reached this cutoff point, capital N, is getting arbitrarily smaller. But is that enough? And we'll find out that that's not enough. Okay, so just to say, if the terms are getting close to A in the real numbers, then they must be getting closer together, right? So this does seem necessary, but it is actually not sufficient enough for the convergence. So it is possible that the terms are getting closer and closer, but yet an diverges. So after you hit some index capital N, and all of the indices little n bigger than capital N, if the consecutive ones are getting closer and closer, that isn't enough to say the sequence converges. So it's possible that it diverges. As an example, consider the sequence of square root of n. This diverges, we know, but we can show that it has this property that we're thinking about as far as for it to converge without knowing the limit, thinking that the consecutive terms are shrinking, their distance is shrinking to 0. So this particular sequence has that property where the consecutive terms are less than epsilon distance, but the sequence diverges. And to show that, here's what's going on. So So we want the property that we're discussing as far as it possibly being a definition for convergence without having to know the sequences. For all epsilon bigger than 0, there exists a capital N where the distance of consecutive terms, an plus 1 minus an, is less than epsilon for all little n bigger than capital N. All right, so to see why this does not work as a sufficient definition, let's consider what it would look like if you had the difference between two consecutive terms. So an plus 1 and an. Well, that's the square root of n plus 1 minus the square root of n. Since square root of n plus 1 is bigger than square root of n, we can just go ahead and drop the absolute value sign. And we know the conjugate of square root of n minus n is square root of n plus n. So if we were to multiply square root of n minus square root of n by its conjugate, top and bottom, right, because this is the same thing as multiplying by 1, just writing it in a clever way, then we get that, it'll be n plus 1 minus n up top, and then divided by square root of n plus 1 plus square root of n at the bottom, which is 1 over the square root of n plus 1 plus square root of n. And that quantity is itself less than 1 over square root of n, right? Because square root of n plus 1 is bigger, square root of n plus 1 plus square root of n is bigger than square root of n. So reciprocate, so taking the reciprocal, 1 over square root of n plus 1 plus square root of n is less than 1 over square root of n. Okay. So for epsilon greater than 0, if we let capital N be such that it's greater than 1 over epsilon squared, then by above, we would get, for all little n bigger than capital N, this distance between consecutive terms, right, which is what we determined to be less than 1 over square root of n by this work above. And since n is bigger than capital N, square root of little n is bigger than square root of capital N. Taking the reciprocal, 1 over square root of n is less than 1 over the square root of capital N. All right, and that's why we have this. And we know n is bigger than 1 over epsilon squared. So replacing this would be less than 1 over square root of, instead of n, it's 1 over epsilon squared. And that results in epsilon when you do that, right? Because you're taking the square root of 1 over epsilon squared. That's 1 over epsilon. And the reciprocal of that is epsilon. Now the point is that we got the difference between consecutive terms to be arbitrarily small, but yet our sequence square root of n diverges. So it is not sufficient enough to say that the difference between consecutive terms, once you've reached this sort of cutoff index, capital N, it's not enough to say that that distance needs to be arbitrarily small. Now it's close to what we need, but in order to fix this, we need to make sure that it's not just consecutive terms. So not just consecutive terms that are close enough to each other by making all of the terms being close to each other past some cutoff value, capital N. All right, so it's just a slight adjustment. We just need this distance or difference to not just be consecutive terms that are past capital N. So for this to work. All right, so here is the definition of Cauchy. So a sequence is Cauchy if and only if for all epsilon bigger than 0, there exists a capital N, so that for all little n in M greater than capital N, we have the difference between AM minus AN to be less than epsilon. So this is an arbitrary indices, little n and M, that are bigger than this cutoff sort of index that I like to call cutoff index capital N, where the distance between the terms is less than epsilon, and that's going to be an arbitrary, any two terms that you pick that's greater than n. So if I had like A1, A2, A3, dot, 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 to get to AN, that's my cutoff sort of thing. So then anything to the right of that, like AN plus 1, AN plus 2, so we could have like our AN be a capital N plus 1, and we could have something like this be our AM. All right, those aren't consecutive terms, but if we, for our Cauchy thing, we need it to be any two terms that we pick that are past this cutoff sort of term index of n. So all of these have indices n and m bigger than capital N. And any two I pick, if I take the absolute value of their difference, it needs to be less than epsilon. And that has to be any two that I pick. So if that's the case for any two that I pick past capital N index, then it's going to be Cauchy. All right, so hopefully that makes somewhat sense. All right, so here's an example. We'll show a sequence whose nth term, so the sequence that consists of the terms that are of the form 7 plus 1 over n is going to be Cauchy. All right, so we're going to show it's Cauchy. And the strategies, we're going to work backwards to find the sum capital N, so that for all little m and n bigger than capital N, we have the absolute value of the difference of the terms AM minus n, AN to be less than epsilon. So we work with this, try to find the necessary value to pick for capital N. So just plugging our indices in, so mn for n, that becomes, this is my AM, and then this is my AN. The 7 subtract out, so you just have 1 over m minus 1 over n, which we can say by triangle inequality, that's less than or equal to 1 over m, absolute value of that, plus the absolute value of 1 over n. So we need the whole thing to be less than epsilon. Well, we can have the whole thing be less than epsilon if each of these two components or two pieces are less than epsilon over 2, since we're summing the 2 up. So we can make each of these less than epsilon over 2. So we would have 1 over m absolute value plus 1 over absolute value of 1 over n to be less than epsilon over 2 plus epsilon over 2. So that way the whole thing is going to be less than epsilon. So we can do this because we can use the Archimedean principle to find capital N such that this capital N is bigger than 2 over epsilon, which taking the reciprocal, that gives us 1 over capital N less than epsilon over 2. All right, so this is the N that we need. All right, and pretty much this is kind of the proof. It just, now I just got to make it just like written better. And here's the proof. So given epsilon greater than 0, by Archimedean principle, there exists a capital N where capital N is bigger than 2 over epsilon. So that means, taking the reciprocal, 1 over capital N is less than epsilon over 2. So then for any little m and n bigger than capital N, we have each one of these. If you take the reciprocals, 1 over little m is going to be less than 1 over capital N. And then 1 over little n is also going to be less than 1 over capital N. All right, so then we use our definition. So am minus an, that's 7 plus 1 over m for the nth term, and then 7 plus 1 over n for the nth term, which gives us 1 over m plus negative 1 over n, less than or equal to the absolute value of 1 over m plus absolute value of 1 over n by triangle inequality. Each of these is less than 1 over capital N, right? Because we have this. And each of these 1 over square root of n, or 1 over capital N, is less than epsilon over 2. So then we have less than epsilon over 2 plus epsilon over 2 to give us epsilon. All right, so the n that we needed was such that it's greater than 2 over epsilon, and that's guaranteed by the Archimedean principle. So since we have am minus an to be less than epsilon for all little m and n bigger than capital N, then an is Cauchy. Right, and that's our sequence is 7 plus 1 over n. So here's a lemma, and the lemma basically is if you have a Cauchy sequence, then it's bounded. All right, so that's a lemma. We're going to prove it in a second. And then we're going to end the video with a proof of this theorem called the Cauchy Criterion for convergence, which basically says a sequence converges if and only if it's Cauchy. All right, so we're going to prove these two, this lemma and the theorem, and then we'll move on to something else. All right, so proving the lemma that Cauchy implies bounded. So how we're going to prove this, I wrote down the idea, and the idea for this is going to be basically the same idea that was used when we showed that if a sequence converges, then it's bounded. So recall that the premise of that whole proof was that if an converges to a, then after some index capital N, all the terms a subscript little n are bounded between a minus 1 and a plus 1 for epsilon equal to 1. So since an converges to a in that proof, we just chose an epsilon value to make it a little bit easier. We just chose epsilon to be equal to 1. So then for all little n bigger than capital N, we know an minus a is absolute value that's less than 1, which basically gives us negative 1 less than an minus a less than positive 1, which gave us that a minus 1 is less than an less than a plus 1. So these are bounds. We have an being bounded between a minus 1 and a plus 1. But that's for all little n bigger than capital N. Now, we do have some terms that come before a subscript capital N. So for all the indices little n less than or equal to capital N, we know that's a1, a2, all the way up to a subscript capital N. And so that's a finite amount of terms. So since that's a finite amount of terms, there's going to be a maximum and a minimum. So one of these might be whatever the largest is. Just say it's, for now, just call it AI. And let's say the smallest is AJ. It might be the case that AI is bigger than a plus 1. That might be the case. And it might be the case that the smallest one is less than the a minus 1 bound for the n's that were bigger than capital N. So it might be that. So in order to be safe, we choose capital U to be the maximum of between the finitely many terms and a plus 1. And then we choose L, like a lower bound, to be the minimum of the finitely many terms, whichever one that is, or a minus 1, whichever of those is the smallest. So therefore, we can guarantee that the entire sequence AN is bounded between L and U for all indices N. And that means the sequence is bounded. All right, that's how the proof was involved for proving that convergence of a sequence implies boundedness. So the proof for this lemma is going to be very, very similar. All right, and again, the lemma, we're trying to prove it's a Cauchy sequence. If it's Cauchy, that implies boundedness. And it's going to be sort of very similar to this, like just using the Cauchy definition. All right, so the proof goes like this. First we got to assume we have a Cauchy sequence AN. Just like in the proof where we did for the convergence implies boundedness, we chose epsilon to be 1. So that's what we're going to do here. And so there exists a capital N such that for all little m and n bigger than capital N, we have that the absolute value of the difference of the terms, am minus an, is less than 1. So since that's for all little m and n bigger than capital N, let's just go for simplicity here to also just fix one of these indices. Let's fix little m to be equal to capital N plus 1. Okay, so then for all little n bigger than capital N plus 1, which is bigger than capital N, we have the absolute value of the difference of a subscript n plus 1 minus an. So I'm just replacing am with that, which we know absolute value is symmetrical, so that's the same as an minus an plus 1. Then using the definition, that's -1 less than an minus an capital N plus 1 less than 1. And then adding a subscript capital N plus 1, we get that same thing, a capital N plus 1 minus 1 is less than an, less than a capital N plus 1 plus 1. So in other words, we found the bounds, right? These are our bounds. For an, where the indices we have is going to be all n bigger than indice n plus 1 that we use for m, which is greater than index n. All right, so we know we have that as our two bounds using Cauchy this time. Just like here, where we had the bounds between a minus 1 and a plus 1, we looked at the terms that come before this capital N, and that's what we're gonna also do here. So we have this time we're gonna look at the terms that come before, in this case, all n less than or equal to capital N plus 1. All right, so we still have a finite amount of terms. And since it's a finite amount of terms, we're going to have a largest and a smallest in this collection of finitely many terms. All right, and similar to the limit for the proof of convergence by boundedness, we're going to pick U to be the maximum of either one of these finite amount of terms, or the upper bound for which we had for an plus 1 plus 1. So these are our finite amount of terms. This is the bound for all the ANs that are between AN plus 1 minus 1 and AN plus 1 plus 1. Similar thing for the minimum. Choose L to be the minimum out of the finite amount of terms, or that lower bound AN plus 1 minus 1. All right, so that guarantees that for any n we have, all of the terms are going to be between L and U. So that means the sequence AN is bounded. Okay, and again, we chose epsilon to be 1 because we know its sequence is Cauchy, so it's true for any epsilon, so just pick 1. And then also for simplicity, since we know it's for any arbitrary indices m and n bigger than capital N, we fixed m to be n plus 1. Okay, so that's the proof for that. Cauchy implies bounded. Now we're going to try to prove the Cauchy criterion, which is if a sequence converges if and only if it's Cauchy. So for the forward direction, we're going to assume AN converges, and let's say AN converges to A. And we need to show it's Cauchy. So we need to show that the distance between AM and AN is less than epsilon for all little m and n bigger than capital N. So we know since our sequence converges to A, then the absolute value of AN minus A is less than epsilon for all n bigger than capital N. So then we can do a trick, sort of, and we can write the absolute value of AM minus AN as the following, where this, we're just subtracting A and adding A because that's 0, or adding 0. So that's our little math trick that we've done in a good bit of proof so far. So it's manipulating what we're going to use for 0. In this case, it's minus A plus A. So that way I can group together the AM minus A and group together the A minus AN. Now each of these is going to be less than some form of epsilon because we know by convergence. So we said this is less than or equal to the absolute value of AM minus A plus A minus absolute value of AN. Of course, you could write this as AN minus A, so that mirrors this. So we know this whole thing needs to be less than epsilon. And since we know the sequence AN converges to A, we can make these two, we can make them as small as we want. In order for the whole thing to be less than epsilon. So since we can make them as small as we want due to the convergence that we already know, make each one of them less than epsilon over 2. So that way we have epsilon over 2 plus epsilon over 2. And we can do that because of the fact that the sequence AN converges. Okay, so that's sort of the strategy. That's kind of the proof. Now here's the actual proof for the forward direction. So assume the sequence AN converges. We need to show that it's Cauchy. So let's suppose AN converges to some number A. Let epsilon be greater than 0. So since AN converges, find capital N so that if you have an index K bigger than capital N, you have the absolute value of AK minus A to be less than epsilon over 2. All right, so that's true for any index that's beyond capital N. So for any little n and m bigger than capital N, we have the following. So we just are using our Cauchy definition here. We're trying to show it's Cauchy, so we got to show that this is less than epsilon. So am minus an, that's where we wrote it as this. This is just adding 0, so it's equivalent. Then we just broke it up as the absolute value of am minus a plus the absolute value of a minus an due to triangle inequality. And each of these is less than epsilon over 2 because we have this. And each of these indices n and m come after capital N. So that's why each one of them we could say is less than epsilon over 2. So that sums up to give you epsilon. All right, so that is the proof in the forward direction. Now we got to do the proof in the backwards direction. So we've proved that if it converges, then the sequence is Cauchy. Now we got to prove if the sequence is Cauchy, then it converges. And I think this direction is a little bit more complicated. All right, so this direction, you need to prove Cauchy implies convergence. All right, so let me just write some thoughts first before jumping right into it. So the strategy. Okay, so we need to prove it converges, and we know it's Cauchy. So we know since it's Cauchy, then for all little n and m bigger than capital N, we have the distance between these terms, am and n, to be less than epsilon. That's something that we know, and that's true for any epsilon. And we're trying to show that it converges. And I'll call it A for what it converges to. So that would mean that we need to show that for all epsilon bigger than 0, there exists a capital N. So that for all little n bigger than capital N, we have the difference, absolute value, the difference of an minus a to be less than epsilon. That's what we're trying to show. And we need to make use of our fact that we know it's Cauchy. So how can we do that? So it's probably going to involve some clever trick where we add 0. So I'll start out with what we need to have is an minus a to be less than epsilon. So let's start out with that. Now I can add and subtract. Let's see, so I can do an minus am plus am minus a, right? So this time, this is just adding 0. And I could do triangle inequality. So that's an minus am plus am minus a. Let's see. There's something I'm missing here because I can't really do anything with this because I would have to know it converges, right? So I have to know which we're trying to prove. So I need to do something else. So that didn't work. Now, let's start over from our toolbox and let me just scratch out. I'll just mark this out. So this was a failed attempt, all right? This is why you do scratch work. Okay, so what can we use? Well, what was the previous thing we just did, previous theorems? This lemma that we just did means Cauchy implies bounded. So we know the sequence is bounded. So that means AN is bounded. And if it's bounded, then let's see. Every bounded sequence has a convergent subsequence. That's the Bolzano-Weierstrass theorem. That's what we're missing. Let's do a similar thing though, what I marked out, but we need to use the fact that we have a convergent subsequence. So AN bounded means there exists some subsequence, let's say ANK, where, let's say this we know converges, so let's say it converges to some value A. All right, and that's using the Bolzano-Weierstrass theorem. All right, so what I marked out is still going to be somewhere I'm about to write now. I was just missing the piece that it needs to be a convergent subsequence. Okay, so I still start out with AN minus A. I want to make use that, well, this means I have A and K minus A to be less than epsilon for any epsilon. So here I'm missing the A and K, so I'm going to add 0, but this time my 0 is going to be plus A and K and minus A and K. So this will be equal to AN, say minus A subscript NK plus A subscript NK minus A. All right, that's similar to what we had here. I'm going to still use triangle inequality. All right, so that's splitting it up using the triangle inequality. I need this whole thing to be less than epsilon. So I have two things that I'm summing together. I need to see, can I make each one of these less than epsilon over 2? All right, that's the question. Well, certainly we can with this. And that's because we know the subsequence converges. So you would find in so that, let's say in 1, we'll make it in 1 and in 2 in the actual proof. So we basically just need to find some index so that for all little nk bigger than that index, then we have, the absolute value of that be less than epsilon over 2. All right, so we can do that just based on knowing that we have a convergent subsequence. Now for this, we can make that less than epsilon over 2. Due to the fact that we have a Cauchy sequence. Right, because this is just two terms of different indices. So find capital N. So for all n, comma nk, bigger than capital N, we have the absolute value of an minus ank to be less than epsilon over 2. All right, and that's how I will do the proof. All right, because we know since it's Cauchy, this should work for any an minus an to be less than epsilon over 2. We're just using specific index value nk for one of these, or nk is arbitrary also at bigger than index capital N. All right, so I think we're good to go ahead and do the proof. All right, so again, we're given A in its Cauchy sequence. Let's epsilon be greater than 0. So let's see. So we have two assumptions that we're going to be using. So since this is Cauchy, and it's bounded, and since it's bounded, there exists a convergent subsequence A and K. Let's say it converges to some value A. And that's because of the Bolzano-Weierstrass theorem. All right, so since this is the case, there exists a capital N, let's say N1, so that for all n bigger than N1, we know that the absolute value of A and K minus A is less than any epsilon, so let's use epsilon over 2. And now I'm going to use, well, we know the sequence A is Cauchy. And this C, so this needs to be in subscript nk. Okay, there we go. So we know the sequence is Cauchy. Therefore, for all little n and m bigger than n2, we have the absolute value of the difference of am minus an to be less. Also, we're going to choose that to be less than epsilon over 2. Since we know it's Cauchy, it works for every epsilon. Okay, and let's pick n to equal the max of n1 comma n2. So that way we're guaranteed both of these Thus, we have for all nk bigger than n, bigger than capital N, we have the absolute value of an minus a, which is equal to the absolute value of an minus ank plus ank, then minus a by adding 0, less than or equal to the absolute value of an minus ank, plus absolute value of ank minus a, and we know this is less than epsilon over 2 because it's Cauchy, and then plus this is also less than epsilon over 2 since we know the subsequence converges. So that's going to sum to give us epsilon. All right, so this is because it's Cauchy. This is because a and k converges to a. And we chose the index capital N to be the max of N1 and N2 so that we're going to guarantee to have both cases in which we have epsilon over 2. All right, and that completes the proof. All right, so that means, so essentially we proved that Cauchy implies convergence. So then that's both directions. Okay, so that's Cauchy sequences. I'll stop the video at that.